Okay, so we should get started. If it gets too dark, just tell me and we can switch the lights back on. But let's jump right in. So my job is to study the invisible. I lead a large international team, and we survey the night sky and harness this information from the cosmos. And with the images that we take, we make measurements, and we use them to try to answer the big questions. So what's out there? What is our universe made of? Why does it look the way it does? And how did it get to being that way? And the beginning and ending of the answers to those questions is dark matter. So my team isn't the first to ask these kinds of big questions. Even ancient civilizations have looked up at the night sky and wondered these kinds of ideas. But we humans can be pretty proud, I think, that we've come quite a long way with our understanding. We've honed a standard model of cosmology, and it does a pretty remarkable job at describing all kinds of observations. And yet, as I hope you'll see by the end of the talk, we also have a long way to go. And I think what's most exciting to me about our field is that, totally biased opinion, I think cosmology, like no other field, has this history of turning our views totally upside down, of defying our expectations and altering the way we view our existence and our place in the universe. And that's what I think is most exciting. So I'll give you two examples to get started of what happened in the past. And you probably are familiar with these, but let's still go with it. So Einstein and Eddington rewrote our understanding of gravity. So the very law that governs everything we know. Is that feeding back, or is that okay? Can you hear me okay? Okay, it's feeding back for me. The very law that governs everything we know. And at the time, scientists were pretty content that they understood gravity and the laws of motion. So if I was holding something, an apple, and I let it go, it would hit the floor. Or if I threw it across the room, we could probably calculate exactly the speed and position that it would land on the other side with. We thought we got it, Newtonian gravity. But this theory, Newton's theory of gravity, even though it was standing up to all the observations that we could make on Earth, once we started to look further afield at larger scales and more extreme environments, then there started to be cracks in this theory. And so Einstein came along and proposed this alternative theory called general relativity. And we talk about that all the time now, but think about it. Somebody came along and they were like, no, we need a new theory of gravity. It sounds totally preposterous. And he proposed that any object that has a mass, then whether it's a planet or a galaxy cluster, it distorts the fabric of our universe. It distorts space-time. And as a result, light from faraway galaxies, as it travels across the universe, the light path gets bent. It also gets distorted. Due to the presence of those objects. So gravity just is this distortion in space-time when things have a mass, and the light path also gets bent with it. And so he predicted that when there was an eclipse, you would be able to see stars that actually lived behind the sun because their lights would be bent due to the presence of the sun. And Eddington went off on expeditions, led these expeditions, and proved his theory to be true. He observed these stars and their altered positions and proved Einstein's theory of general relativity. And this is the bread and butter of an astrophysics degree today, but look at the New York Times headlines. It's like, lights all askew in the heavens, and men of science more or less agog. So it really was a blow to the way we understand our universe. And another example of this was in the 1970s when Vera Rubin was observing the effects of dark matter. So she studied, we didn't know about dark matter back then, she studied the motions of stars in spiral galaxies. And if you think about it, the faster a star is moving around, or the faster a planet is moving around in orbits, the same idea, then you need more gravity, you need more stuff keeping it glued in together so they don't fly apart. And so she expected to observe these stars and see the dashed line in the top right plot. And what she observed were the blue data points, and the line fitted to it instead. So she saw that all the stars were going much faster than she expected. And so what does that mean? You can take all the stars and count them all up and deduce the mass of the visible stuff in the galaxy, the mass of all the stars. And that couldn't compare to the mass that you would need to let them maintain that speed. So if you needed them to not fly apart, then you needed much, much more mass in the galaxy. And so she postulated that there was some invisible mass in the galaxy, and we call it dark matter. And it's very strange. It doesn't emit or absorb light, so it's invisible. But we know that it's there from the effects that it has on things that we can see. So we now know that dark matter comprises of more than 3/4 of the mass in almost all galaxies. And as you can see here, it forms this kind of blue, it's not blue, it forms this stable halo in which the visible galaxy can live. So that the visible galaxy is very small and it lives in this big blob of dark matter. And it creates that nice sturdy home. And so dark matter kind of acts as the glue to keep all the stars together. And so it really is the building blocks for the universe and for galaxies and structure in our universe that we observe. And so this is another totally important finding that we really weren't expecting. And I hope that the story that I'll tell you about also ends in the same way, where it pauses us to think. So let's take a step back and think about what we know about our universe today. So time and time again, this universe has surprised us, and none of these things came easily, and sometimes they came with wild resistance. But slowly and through the power of science and peer-reviewed research, they were proven to be true. So I hope these examples kind of show you that we have to keep an open mind when we're thinking about our universe and let the research, let the data tell us what it is, what's there. So as I said, I'm hoping that the story that I tell you tonight will end like these last two stories, where they make us step back and think a little bit harder, think about what we know and what we don't know, and rethink our ideas of the universe. So let's recap what we know. We know that 13.8 billion years ago, the universe was just this hot, dense soup of particles. So particles flying about, and there were very tiny fluctuations in the temperature and the density of these particles, just random fluctuations governed by quantum physics. So some of the particles might have been slightly hotter, some slightly colder, some closer together than others, totally random. And then the universe underwent this period of rapid expansion, and it left an imprint of those fluctuations at the time. And that's what we measure with the cosmic microwave background. So this is a snippet of the map of the cosmic microwave background as measured by the Planck satellite. And some of the different color tells you the slightly different temperatures, very small temperature fluctuations. And that's the first light of the universe, the first light that was emitted. And what we found with this expansion of the universe is that the expansion of the universe marched on, and those very tiny fluctuations cooled and expanded and seeded the large-scale structure that we observe today. So the parts of the cosmic microwave background that were slightly more dense eventually formed the first stars, the first galaxies, now today the biggest galaxy clusters. And the parts of the soup of particles that were slightly less dense formed the cosmic voids today. And so that random pattern is imprinted in what we observe in galaxies and in the large-scale structure today. Now, so when you look at this diagram, you're looking at time going that way and distance away from Earth going that way. So the expansion of the universe marched on in time this way. Now, we can use our standard model and replicate our universe's evolution in computer simulations. So this is a snapshot from a simulation made at Stanford University, shown in the bottom right-hand side. And these two pictures both capture our universe. It's the same universe, just at very different stages, from first light to present day. And this is the foundation of our standard model. It is an astonishingly good description of our universe as we observe it. And it's pretty simple. We can model this whole evolution with 6 parameters. So our standard model of cosmology means that we spend a lot of our time just trying to measure these 6 parameters. And with that, we can describe the evolution from a soup of particles to galaxy clusters and galaxy voids on epic scales. Now, what's the catch? What's the catch? What's wrong with the standard model? Well, there are 3 components to this model, and we know that everything that we are familiar with, you, me, the stars, the gas, the black holes even, they are visible matter. So they make up 5% of everything we know. About 1/4 of the stuff is dark matter, and about 2/3 of it is dark energy. Totally different to dark matter, and we're not going to talk about dark energy today. Let's just focus on the dark matter. Now, it's really quite remarkable that in our insignificant existence as humans, in this grand story of the universe, we only occupy a very small amount of time, and we've made all types of different observations that fit this model. So whether it's exploding stars, supernovae, or bending light, which is gravitational lensing, or even, mapping the velocities of galaxies in the universe, or measuring the first light of the universe, they're all pretty well described. These very different observations are all very well described by our standard model. And so it's an undeniable success story. But the elephant in the room is that in this model has dark matter, and we don't really know what dark matter is. We have even less of a clue about dark energy. And so it's pretty awkward because we're talking about not understanding 95% of our universe, and yet we claim to be experts. So it's a very strange situation because despite the elephant, our model keeps holding up to whatever observations we throw at it. So our instruments and our techniques, they're getting better with better technology. So we make more precise measurements, and we keep throwing them at this model, hoping to find cracks or clues or some idea, some hint of how to rework the standard models or how to learn more about dark matter. Now, we know that our universe is a cosmic web on epic scales. When you zoom out large enough, you get this web-like structure. So in the simulation shown here, and we see the same kind of pattern in the data, there's this complex web structure in the black, that's the dark matter. And the visible light, the luminous light, things like galaxies and stars, they live where the dark matter lives. So the dark matter kind of forms the bones of the universe, and it dictates where the luminous galaxies live. It's kind of like the galaxies of the universe are Christmas lights wrapped around this invisible dark matter scaffolding. And so dark matter does the job of forming the structure of the universe. It's crucial to structure formation, and it does the job of gluing galaxies together. Now, when I talk to my parents, sometimes they're like, what is this dark matter? And it totally sounds like hocus pocus, or something that we really just don't need to care about here on Earth. But the truth is that dark matter, without it, our universe just would not have evolved to the way that we observe it today. So I'm going to show you two snapshots of computer simulations side by side, and they were set off to evolve, and one of them, the one that's shown here, is very similar to our own. It has the same amount of dark matter that we think we have. And what we observe is that it gets clumpy quite quickly. And it's a universe in which it's really easy to form galaxies in this universe. On the other hand, when we make a simulation which has less dark matter, like this one on the right-hand side, not that much seems to happen. So the things that start out like small clumps stay small. In this universe, the one without so much dark matter, you don't get anything that looks like our galaxy or like any other galaxy. You wouldn't get the Milky Way, you wouldn't get the sun, and you wouldn't get these cozy homes like our galaxy for our planet to form. So our home just simply couldn't exist in a universe that didn't have the right amount of dark matter. And that's because our universe was kind of concocted with the most precise recipe. So I don't know about you, but I bake terribly, and I always try to change the recipe. But in this recipe that we need for the universe, there's no recipe replacements. There's no adding this and that. Because without a very particular amount of dark matter, we just wouldn't have had enough mass in the early stages of the universe to seed the structure of galaxies, to start forming galaxies, which became the comfortable hosts for planets like our own. So we need dark matter, and we know it exists from its impact on the things that we can see. But what is it? We don't know. So particle physicists are on the hunt for this dark matter particle, and there are all these intricate experiments all around the world, deep underground or wherever in lakes. And though we have pretty good guesses, we have educated guesses for what we're looking for, the fact remains that there's no particle yet. And so cosmologists come at this from a different angle. So we study the universe, and we learn about the properties of dark matter. And we use that to narrow down a list of possible models for dark matter. And really, there are more models on the market than we can count, with ridiculous names. So some of them are fuzzy dark matter, wimpy dark matter, machos, self-interacting dark matter, warm dark matter. There's basically, if you think of a name, it probably exists. But the problem is that none of them really fit the bill. None of them seem quite right. And so as a cosmologist, we can tell you where the dark matter is, and we can tell you that it behaves quite like normal matter with respect to gravity, but it doesn't interact with light or normal matter, so it's invisible and it would fly right through us. And so how do you learn about that? How do you learn about something that you can't see, you can't touch? Well, one answer is weak gravitational lensing, and that's where I come in. So if you imagine a faraway galaxy, its light journeys across the universe, and the light path gets bent. This is Einstein's theory of general relativity. The light path would get bent. And that's because clumps of matter distort the very fabric of the universe. Like these blobs are clumps of matter, like some big cluster or dark matter lump, and it distorts the fabric of the universe, this orange grid, this space-time. And the path that the light is traveling along gets bent with it. And this is the consequence of general relativity, and it means that every image that we take of a faraway galaxy is ever so slightly distorted with the imprint of the cosmos between us and that galaxy. So, for example, galaxies whose light travel past the same structures in the universe, they get coherent distortion. So they kind of get aligned with each other because they get distorted in the same way, like the two galaxies on the left-hand side. Their light path gets bent the same way and they end up aligned. Now we think that if we can measure these tiny distortions, this is really exaggerated, it's really much tinier than that, with extreme precision, then we can learn about the universe that the light passed through, that chunk of universe that the light traveled along for billions of years. We learn about it, we learn about the properties. So it's just like how your glasses have a lens in them, and that lens bends light to correct an image. In this case, the lens is gravity, so it's called gravitational lensing. It acts like the lens to background galaxies. And the effect is really small, really small. So we call it weak gravitational lensing. And that's the technique that we use to learn about dark matter. So because the effect is so small, we need a lot of galaxies to be able to make the measurements. And we can use weak lensing to tell us where the dark matter is. And it's kind of like our eyes can only see normal light. And then we do weak lensing, and it lights up where the dark matter is for us. It lets us put on these special revealing glasses. And we think this probe is extremely powerful. It's been demonstrated to do that. It tells us where dark matter is in our universe. It helps us map it out. And the best experiment to do weak lensing with at the minute is the Dark Energy Survey. So this is our telescope here. The naming is confusing because our survey also studies dark energy, but for the purposes of this talk, let's just call it the Dark Matter Survey. Now, I lead the weak lensing team in this experiment, and we have scanned 1/8 of our night sky, taking data for 6 years, and we've harnessed information from the cosmos, slowly building up a deeper and deeper image of 1/8 of our night sky. And my team comprises of scientists from all around the world, so science can no longer be portrayed as this lone man scribbling over his parchment. These groundbreaking experiments will change our understanding of the universe, and it requires teamwork. And together, we just analyzed the first half of the data set, so 3 years of data. And this is the state of the art in the field. So for 3 years, we tinkered over the images. We made these intricate measurements using more than 100 million faraway galaxies. So that's 4 times more than the next leading experiment, 100 million. And we fine-tuned our methods to be able to handle this enormous data set. And this is what we're after. So we take our observations and we compare them to the same model that is so well described by the cosmic microwave background. So the cosmic microwave background observations of that light are the gold standard of the field. They really installed our standard model. They were an excellent fit to the standard model, and they really bolstered it. And so when we do this comparison, we set up quite a beautiful end-to-end test. So we're asking, can we use the same picture that fits the seeds of our universe to describe the vast structures that formed 13.8 billion years later? And so does our model, with all of its dark matter and strange things, does it correctly describe the evolution of the universe between these two very different stages? And now it's a particularly exciting time in cosmology. So let me set the scene for you. Technology has rapidly grown, and we have the most powerful telescopes in the world, and there are several teams doing weak lensing measurements. 3 teams right now. And we use much larger data sets than ever before, and we're really desperate to see if what we find is consistent with our standard model, or maybe we find cracks in that picture. And our results are strange. They're not quite what we'd expect. So these are the headlines that came out when we released our results. And so my first thought when we looked at the results were, what did we do wrong? But no, I have a team that I can rely on, and we've done so much hard work for 3 years testing our measurements and making sure that everything was correct. And so it really is intriguing so intriguing that we're spending another 3 years analyzing the second half of the data set to do an even more stringent test of our model. But what's exciting is that it's not just our results. So we see similar results from the other 2 experiments around the world, hints that maybe our standard model isn't quite right. So, with 5% of the universe understood, there's a lot of wiggle room for improvement. And maybe our results are pointing to the next missing piece of the model. Maybe it's pointing to new properties of dark matter. Or maybe we're on the cusp of something, the next big scientific breakthrough. But I'm getting ahead of myself. Let me backtrack. So it's Christmas Day, and you take a short flight over the mountainous Coquimbo region to La Serena after a much longer trip to Santiago, Chile. And then it's a rickety van ride back and forth up the mountain on this dusty, dusty track through the desert. And you climb 2,200 meters of Cerro Tololo. And every corner is more exciting than the last. You're excited to get to the telescope. You know what you're getting with the data. You know you're going to find interesting things. And up there, it's high, it's dry, and it's smack bang in the middle of nowhere. And that's exactly what you want for an observatory. And for astronomers, this is no secret. Every direction that you turn at the summit, there is another telescope. So you look further afield on other mountaintops, and there's nothing there as far as your eyes can see. And at the summit of the mountain, the barren land feels otherworldly. There are eerie colors, sweltering daytime temperatures and cold nights. UV warnings are signposted everywhere, telling you to wear sunblock. And we have our little man-made white domes scattered around. It really does look like living on another planet. And there are so many domes around, but they all pale in comparison. So this is the Victor Blanco telescope, and it's the king of the mountain. It's the tallest, and it's simply gigantic. And it's the home to the Dark Energy Survey. So nestled on the 4th story of this building is our 4-meter primary mirror. And that's because, it's a big mirror, and that's because telescopes run under a pretty basic principle, which is if you put a bigger bucket of water into the rain, then you'll collect more rainwater. And that's exactly what we're doing. If we make a bigger telescope, then you collect more and more light from the universe, from light from galaxies that have traveled across the universe to get to our telescope. Now, this is the camera that we use. It's the Dark Energy Survey camera. It's also huge. The lens is 3.3 feet, and it consists of 74 super sensitive CCD chips with a total of 570 megapixels, but on an enormous scale. And it's extremely high maintenance. It requires a 24/7 stream of liquid nitrogen to keep our CCDs at a healthy minus 100 degrees Celsius. But it's totally worth it. This piece of kit allows us to image a patch of sky about 14 times the size of the full moon to exquisite resolution at each pointing. So every time we point at the sky, we get 14 full moons. Now we're there to work, so that means it's kind of a race against the sun. As soon as the sun sets, you try to get as much data as you can from the universe before the morning light starts creeping in, and then you're forced to pack up and go to bed. But observing life is pretty special. There's an afternoon meeting up at the telescope where you decide what you're going to observe, which patches of sky. Then you dash back down to the lodge and get some dinner. And then there's a sweaty trek back up to the mountaintop again to get organized for the night. And once you're ready to go, it gets calm, as long as there are no disasters. And the observers on the mountains, all the observers on the mountain, they quietly emerge from their domes to watch the sunset. And sunset is a pretty spectacular event there, and it's a well-established tradition that all of the observers come out to watch the sun go down. And what was most intriguing is that humans aren't the only ones who've noticed. So the visachas of Cerro Tololo, there are something like kangaroo rabbits. They come out from their homes, they gather at dusk and watch the sunset as well. I kid you not, I didn't believe it until I saw it. But it's hard to believe the tale, but sure enough, day after day, at sundown on the summit, astronomers and visachas are both wide-eyed facing west, watching the sunset. And the noticeable quiet at the mountaintop is broken a few hours before sunset as these large domes creak open and the telescopes kind of start moving about, and they look quite like guardians of the sky. They're all perched on the summit. They all open and awaken at the same time, these giant robots, opening their eyes and peering into the cosmos. And throughout the night, they rotate slowly, doing their work, searching the night skies. And we just tiptoe around them with our tiny headlights in the dark, taking what we can to learn about our universe. Now, what do we see? Well, you can see all kinds of things with the Dark Energy Survey camera. So if you are like Elon Musk and you've lost your Tesla, we can observe it in our images. So that's it there at 3.5 million kilometers away from Earth. And if there was an earthquake the night before, we can also tell you. So I'm really glad I was not on that observing button at the mountaintop. But of course, what we're after are galaxies. So we have those 74 CCDs. So this is one of our stacked CCD images. And it doesn't look like much. But when you zoom in to any one of these tiny specks of light, each one is this beautiful galaxy that no one has ever seen before. It's totally kind of magical to think about. And I worked it out one night that I was there. Okay, if we take this many exposures and if we're pointing at this many patches of sky, how many galaxies can we observe in one night? And the answer is about 1 million if you have good weather. So every single night we observe 1 million galaxies, slowly building up this image. And when you zoom in, each of the tiny little blobs are these beautiful galaxies, not stars. So here are some particularly big Dark Energy Survey galaxies. And you can see that they really come in all shapes and sizes. And when we do our analysis to learn about dark matter, we need 3 pieces of information. So we need how far away the galaxies are, their locations on the sky, and the shapes of the galaxies, so that we can estimate how distorted that shape is. Now, this doesn't sound so hard. I started my PhD some years ago, and I was told, you have to measure shapes and distances to galaxies. And I was like, sweet, got it. But the galaxies that we're dealing with aren't quite the picturesque spirals in the front, but rather these like funny, fuzzy little 2-pixel blobs in the back. Those are the ones that we're really after. And the light particles from these galaxies travel all the way across the universe, encoding the lensing, these secrets of what the universe is made of. And then they get to Earth, and the Earth's atmosphere ruins our images. And then it gets ruined a little bit more in our detectors. And so really what we're measuring are shapes and distances to these fuzzy blobs of a few pixels of light. And the challenge gets harder than that, because we can actually do this pretty well for one fuzzy blob. But the challenge that we're hitting now, we call it blending. And it's because our data has gotten so good that we can see galaxies so far away that now every time you look at a galaxy, you're really kind of looking at lots of galaxies all sitting on top of each other along the line of sight. And that's really causing a problem for us, that it's hard to disentangle the light from these galaxies and tell how far away each of these galaxies are. And, I spend so much of my time thinking about galaxies and working with them. And the truth is that I really don't like galaxies. I never liked them. I never really wanted to study them. They are merely pawns in our analysis, because what we care about is dark matter. So we just use the galaxies to tell us where the dark matter is. So this is a map of our universe, of our night sky. So the same way we project the map of our globe, of our sphere onto this shape, it's the same thing, but pointing up. And so the Milky Way is kind of stretched. It doesn't look vertical because of the projection. And this is what we've mapped. So they're the small and large Magellanic Clouds down there and the Milky Way. And that's the dark matter that we've mapped. So the lighter bits have more dark matter and the darker bits have less dark matter. And you can see that web-like, that cosmic web pattern. And it's the largest dark matter map ever made. And so, then fine, we can make these pretty pictures. But what else can we do? We can tell you where the dark matter is, what it looks like, how clumpy it is. But really, we don't care about these pretty pictures either. We use the data to tell us about our standard model of cosmology and to test that model. And our computer pipelines are like an industrial machine. We make our measurements and then it crunches these, comparing them against all different types of models, and then kind of tells us the results at the end. It's constraining those 6 parameters. Now, in those parameters that we need to describe our model, one of them, or 2 of them, when you combine them really, tell us about how much dark matter there is and how clumpy that dark matter is. We call it S8. And S8 is pretty topical at the minute, because when we look at this parameter, we get results that don't agree with the early universe. So I'm going to show you a plot now, and I'll walk you through it. This parameter, its value is on the y-axis. We don't really need to know what the value is, but that's the measurement that you get from the cosmic microwave background, from the earliest light of the universe. Now, when we add weak lensing to this plot from all the different surveys, this is before we looked at our results in the dark energy surveys, so this is what everyone else gets, you can see that they all sit below the yellow band. And that's weird, because if they agree with each other, some should be higher, some should be lower, they should fluctuate around the model. But we found that they're all lower, and so we were kind of stuck in the dark energy survey wondering what we would see. Would we see the same thing, that we predict a discordant universe, it disagrees with the standard model, or would we find consistency? And this lowness has existed from almost every weak lensing data set. So people have been really quick to ask, well, what have you done wrong? It's always what we got asked in previous iterations of the analysis. And maybe that was fair at first, because weak lensing is a pretty new tool, and the data is really challenging. But really, in the last 5 years, we've started to hone our methods, and we have much better data, and we have these independent teams doing the same thing. And so the evidence is getting pretty hard to ignore. But still, we knew there would be intense scrutiny on our measurements. So we did what we called a blind analysis. And I think this is the most important part that we really should communicate. We know that we're biased. Even though we're scientists, all humans are biased. I'm a young scientist. I'm pretty new to the field. It might be that I don't want to cause a stir. I might just want to get my experiment to agree exactly with what everyone says it should be, just to live a simpler life. And so it's not hard to imagine that I might make decisions that aren't totally unbiased in my head. And that kind of bias isn't good, because we're supposed to be objective. And so to get around that, for 3 years, we did our experiments. For 3 years, tinkering with the data and making measurements using fake data. So we collected all this data and we never touched it. We made fake measurements, and we calibrated and made all of our analysis choices without ever touching the real data. And this is what we call a blind analysis. And then when we were absolutely sure of how to calibrate our data and how to choose this model or this model, then we hit go and reran the analysis with the real data. And we still don't get to look at the results when we hit go until we get the entire team of 250 scientists all onto a call to look at the results. So cue the self-worry and the imposter syndrome. You have the most important presentation of your life, and you have no idea what you're going to present. So this is what we found, the green line here. And so, this is the most powerful data set that exists for this type of measurements. I know my team was careful, we were unbiased, and yet again we find that our results don't really agree with what the early universe dictates. And in cosmology we call this a tension, the S8 tension. And scientists are pretty hyped about what this means. So what could it mean? We have 3 options. Either the cosmic microwave background measurements are not quite right. And I don't know how many talks you've come to here, but those measurements were led by Cambridge, and so we really don't go around saying that when you live in Cambridge. Option number 2, something's not quite right with the weak lensing measurements. But there are now 3 teams, and we don't really speak to each other when we're doing our analyses, and we all do our analysis in this blind way, so it's really hard to imagine that we've all missed the same thing. Or maybe this is new physics. Maybe this is a sign that we need some new property of dark matter, or some modification to our standard model to be able to explain this discrepancy. And so now that we have better data, we have the second half of the data, we're going to keep testing this. We're going to keep looking. But here, I've teamed up with George Estafio, who led the Planck CMB experiments. We finally stopped arguing over whose experiment was right and whose experiment was wrong. And we were like, okay, let's say both of our experiments are right. What could it be? And we published a paper last year that I'm pretty excited about. And now we have a team with 2 students and other people at the IOA who are tackling this question and trying to understand. And what we think could be the answer is that maybe we need something that suppresses power on small scales in the universe. And what does that mean? Well, it could be that we need some kind of new dark matter model, like, for example, the axion dark matter or self-interacting dark matter. They would all do this. They would give you less power than you expect on small scales, and less clumpy universe. But it could be, the other option, is that we don't really understand galaxies. As I said, I don't really like them, so now I'm spending a lot more of my time learning about them. And so galaxies, they have these active galactic nuclei. They spew out energy in jets that are in these energetic processes, and it kind of redistributes all the stuff in the universe around it. And it could be that we don't really know how to model those very well. And so that's why we've kind of teamed up with other people at the IOA, like Deborah Sajaki, who's an expert in galaxy formation, and we're trying to understand, which is it? Is it that we just don't really understand galaxies and we need to know better how they live and how they formed? Or could it be that this is the smoking gun for dark matter? And we're really excited to find out. Until then, we're doing it all again. So we have the second half of the Dark Energy Survey data. We'll have 200 million galaxies in that data set. And still, that's not the end, because really, we're just training ground in this survey. We're all just testing and getting ready for the big surveys. And that is Rubin Observatory, which is one mountaintop over in Chile, and Euclid Space Telescope and Nancy Grace Roman Space Telescope, which these two will launch to space, as the name suggests. And Rare Rubin is going to be absolutely epic. Well, the three of them will be epic. We are at the dawn of this totally game-changing decade for cosmology. In a couple of years, we'll open these new telescopes in the next few years. And just in the first year of observation, Vera Rubin will give us 1 billion galaxies. So we really have to do better at honing our methods and honing out the way we make our measurements to get ready for these experiments. That's what lots of the work is right now. And with these incredible advancements in our technology and in our instruments, there are just so many exciting prospects in the coming years that it really is genuinely hard to think about what our standard model will look like in the next 10 years. What will change when we have all of this data in hand? And so cosmologists are really just totally spoiled getting ready for this new era. Our standard model has been standard for a couple of decades now, but I think we're at the dawn of something new, and I can't wait to see how our understanding changes. And there's one thing for certain, which is that we won't always only understand 5% of our universe. If not in my lifetime or the younger people's lifetimes, there's a bright future ahead with all of this data for us to understand better what our universe is made of. And I think that we need these new bright minds to come and help us think of the next paradigm shift in science. And even then, I'm sure there'll still be more pieces of the puzzle to solve. So I encourage you to look up and keep asking questions. Thank you.